Okay, so we're going to take a look at another question from the topic of electromagnetism. We're told an electron with kinetic energy 1.2 kiloelectron volts circles in a plane perpendicular to a uniform magnetic field. The radius of orbit is 30 centimeters. Find the speed, the strength of the field, the orbit frequency, and the period of the orbit. Okay, so first we're going to find the speed. In order to find the speed, we need to use kinetic energy. So kinetic energy is 1/2 times the mass times the velocity squared. If we rearrange this for velocity, this tells us the velocity is the square root of 2 times the kinetic energy divided by the mass. Now we've been given the kinetic energy in terms of electron volts, and we need to convert this to joules. So the way that we do this is if the kinetic energy is 1,200 kiloelectron volts, to convert it, we'll be multiplying it by 1.602 times 10 to the minus 19. So this will give us 1200 times 1.602 times 10 to the minus 19, and we get 1.922 times 10 to the minus 16. So now we're going to use this kinetic energy. So we find that the velocity is the square root of 2 times this kinetic energy, 1.922 times 10 to the minus 16, all divided by the mass of the electron, which we know is 9.1 times 10 to the minus 31. So then we put this in our calculator. Square root 2 times 1.922 times 10 to the minus 16, all divided by 9.1 times 10 to the minus 31. This gives me something along the lines of 2.05527 ... times 10 to the 7. This is a velocity, and so this is going to be in meters per second. So this is the value that we're after for this first question. Now for part B, we're told to find the strength of the field. Well, we know this is moving in a circular orbit, and we have a formula linking the magnetic field strength with other variables in that case. So we know that the radius of the orbit is equal to the mass times the tangential velocity divided by the charge times the magnetic field strength. We can rearrange this for the field strength. We get the field strength is mass divided by tangential velocity over charge times the radius. So this gives us the field is going to be the mass of the particle, which we said was an electron, so 9.1 times 10 to the minus 31, multiplied by the velocity. Now this is 2.0, let's call it 0.55 times 10 to the 7. We're just rounding these crudely, it's perfectly fine. You can round these however you want. We're just getting approximate values anyway. Divided by the charge. Now because it's an electron, this is minus 1.6. Minus 1.6 times 10 to the minus 19. Yep. Multiplied by the radius of the circle. Well, this is 30 centimeters, so that's 0.3 meters. So now we're going to find our magnetic field strength. So we get 9.1 times 10 to the minus 31 times 2.055 times 10 to the power of 7, all divided by minus 1.6 times 10 to the power of minus 19 times 0.3. My calculator tells me this is about minus 3.895 ... times 10 to the minus 4. And this is going to be in Teslas. And you could write this as a positive if you want. The orientation of the field doesn't really matter. One orientation will spin the particle one way, another orientation will spin the particle the other way. It depends how you look at it. It depends how the field is oriented. So This number could be made positive, and that answer is equally correct. They're both correct. So now let's have a look at part C. We're asked to find the orbit frequency, or the orbital frequency. Well, we know this travels in a circular path, and if something's going in uniform circular motion, the frequency is its tangential velocity divided by its circumference, which is 2 times pi times the radius. Its tangential velocity was about 2.055 times 10 to the 7. Its radius is 30 centimeters, so this will be 2 times pi times 0.3 in meters. So therefore, the frequency that we're going to find here is 2.055 times 10 to the 7 divided by 2 times pi times 0.3. My calculator tells me this is 1.0902 ... times 10 to the 7. And this frequency will commonly be represented as hertz. So this is the answer to part C. And then the last part we're asked about is the period of the orbit. So because we've just found the orbital frequency in hertz, we actually have a shorthand formula for the period. We know the velocity and we know the circumference, so we can do this a few different ways, but we know that the period, denominated t, is equal to 1 divided by the frequency. So we're just going to use this shorthand formula because we have already found frequency. So this is 1 over 1.0902 times 10 to the 7. 1 over 1.0902 times 10 to the power of 7. This is about 9.17 ... times 10 to the minus 8, and this is going to be in seconds. So this is how long it takes to do one rotation. So this is the answer to part D. So this is how we do this question. This is a very interesting exam style question. It has lots of parts. The later parts you find work on the earlier parts. So if you didn't get one part, it then gets more difficult to get the other parts. Very common in a high school or first year university style exam.